Hi, I'm Tushar, a student of IIIT Delhi. Today, I'm going to present a research paper study on explainable AI decision model for ECG data of cardiac disorders with my partner Atul, who is also a student of IIIT Delhi. It was done under the guidance of Dr. Anubha Gupta from the Department of EC, IIIT Delhi, and Dr. Manu Shetty from the Department of Pharmacology, MAMC Delhi. Our paper has been published in the Biomedical Signal Processing and Control Journal this February. The objective was to develop and implement an interpretable AI model for screening patients with heart disease using ECG in various healthcare centers where there could be a shortage or unavailability of cardiologists. The explainable AI model explains the model decisions, therefore helps to develop the trust of a doctor in using our model. Before we go further, let's first understand what an ECG is. An ECG or electrocardiogram is a graphical representation of electric potentials generated by the heart. ECGs are quick, safe, non-invasive, cost-effective and painless test commonly used for the identification of cardiac abnormalities. As we can see in the figure 1 of a poster, it consists of different waves, namely P, Q, R, S, T and U. These potential differences are measured using 12 LEDs placed at different parts of the body. We have used the PTB-XL ECG dataset, a large publicly available dataset, as the primary dataset for building a deep learning based cardiac disorder detection model. It is a 12 LED multi-labeled ECG dataset consisting of 21,837 patients, samples over 5 classes, namely conduction disturbance, hypertrophy, myocardial infarction, normal ECG and ST and T change. These 5 classes are from 24 subclasses such as left posterior fascicular block, incomplete left or right bundle branch block, left or right ventricular hypertrophy and anterior or inferior myocardial infarction. Here we have carried out classification of 5 superclasses, also called as the target classes. Also, I want to clarify that multi-label data implies that a sample can belong to more than one target class. Figure 2 displays the class distribution of this dataset. Now, many a times, models perform exceptionally well on a dataset but fail to perform well on other datasets with similar characteristics. So, we utilized another similar ECG dataset of arrhythmia patients to test the generalizability of a model performance. We trained and tested various models on the datasets. We started with spatiotemporal CNN, also known as STCNN8, which consisted a total of 8 temporal layers, 1 spatial layer, 2 dense layers, and finally a sigmoid layer as output. Here, the temporal layer denotes kernel and pool sizes were along the lead, and in the case of spatial layer, they were across the leads. We added 2 skip connections to this model and reduced the temporal layers to 5 to reduce model parameters, thus creating the STCNN5 model. Now in our best performing model, shown in figure 3, namely STCNN gap 5, we used global average pooling in the last convolutional layer to drastically reduce the total number of trainable parameters. Apart from that, we have also benchmarked some popular models such as the ResNet, bilinear CNN, SCNet and Attention 56 on the same dataset. We trained our best model on another publicly available arrhythmia dataset as well with hyperparameter tuning. It achieved great performance which was comparable to its state-of-the-art models. So often, CNN models are considered as black boxes due to the lack of interpretability of their internal working. To counter this, we have used Shapley Additive explanations, which are also known as SHAP, gradient explainer, to provide visual explanations of the predictions made by our best trained model. SHAP assigns importance value to each feature based on its impact on the output prediction. For example, left anterior fascicular block is a type of condition disorder of the heart. Patients with this disorder have increased chances of heart failure or sudden cardiac death. Now our AI model clearly classifies this disorder using ECG. As seen in figure 7 of our poster, the ECG segment highlighted RS wave of LED 3 in red color, the most important for the diagnostic segments of the ECG for this heart disorder. Meanwhile, the features with lesser importance are highlighted in blue color. The highlighted portions for each class are also consistent with the diagnostic criteria of the respective cardiac diseases. Now I would like to discuss the main results of our study. The classification performance of different models is displayed in figure 6 of the poster. Our ST seen in GAP 5 model, having a total of 165,000 parameters, yielded the best performance and it is highlighted in this figure. AUC score, which is area under the curve, was a primary evaluation metric as it was for the state of the art. We achieved an accuracy of 89.73% and an AUC score of 93.41 on the test set. These results even beat the existing state-of-the-art results on the same dataset. Now it could be credited to the out-of-the-box ideas applied to the architecture, resulting in superior performance as well as SHAP interpretability. This interpretability works as the validation of the efficacy of the proposed model. It could also be confirmed that from the TSNE plots shown in figure 5, the distinguishable clusters as we move from the first convolutional layer to the last convolutional layer. Now, interpretability of the automated ECG model augments the confidence and effectiveness of cardiologists in diagnosing heart disease accurately with less human error, especially in overloaded healthcare setups in low, middle income countries such as India. I would like to conclude by saying that the interpretation of the model by SHAP for multiple heart disorders highlighted the same segments of ECG waves as would have been analyzed by an expert cardiologist while inferring a heart patient. Thus, a proposed model can easily be integrated with the existing ECG machines, mainly to help doctors in primary and secondary healthcare centers to effectively and accurately diagnose patients or refer them to cardiology centers for further treatment. Lastly, we have also made an open source web application for anyone to detect ECG samples of cardiac disorders, which is available at ecgdetect.sbilab.iitd.edu.in. Thank you.